Right now, space itself is stretching fast. We're talking about 700,000 miles per hour. Galaxies are being pulled away from us at such high speeds that some even move faster than light. But they're not flying through space. Space itself is expanding, growing larger with every second. And here's the mind-bender. The universe isn't expanding into anything. It's just making more space as it grows. That alone rewrites everything we think we know. Why does every part of space act like it's the center of everything? What's the strange force that makes up 70% of the universe? And what does all this say about how and when the universe might end? If you're ready to rethink reality, hit that like button, because we're just getting started. Space isn't still. Imagine the gaps between galaxies stretching like a giant, invisible fabric. Even the space to the nearest star is growing, bit by bit. Space is not nothing. It's the stage where physics plays out. It can bend, ripple, and most surprisingly, expand. Now think of a balloon. As you blow it up, the surface stretches and every point on it moves away from the others. But here's the twist. Our universe isn't expanding into something. It is everything. There's no outside. It just stretches itself from within. Now take that balloon idea, but in 3 dimensions. That's what's happening in our universe. It's not growing into empty space. It's creating more space everywhere. This is called intrinsic expansion, space growing from within, not outward into a void. But this doesn't pull everything apart. Inside galaxies, gravity still wins. Atoms hold together. But between galaxy clusters, space stretches so much that nothing can resist it. In fact, every second, a region 1,000,000 light-years across grows by 22 meters. That's why galaxies millions of light-years away seem to race off at incredible speeds. This all started with Edwin Hubble in 1929. He found that galaxies outside our local group are all moving away, and the farther they are, the faster they go. At first, it looked like we were at the center of the universe. But we're not. Every galaxy sees the same thing. The universe began expanding 13.8 billion years ago, when space and time themselves first came into existence. Back then, everything was packed into a point smaller than an atom. Today, that same region spans billions of light years. Hubble also made a shocking discovery. Galaxies weren't just drifting. They were fleeing at impossible speeds. He measured their movement using light. Each element gives off a unique color when heated, like hydrogen glowing red. But Hubble saw those colors stretch toward the red end of the spectrum. The more distant the galaxy, the more its light shifted. This redshift proved galaxies were moving away, and fast. He discovered a pattern: double the distance, double the speed. This became known as Hubble's law. The farther away a galaxy is, the faster it recedes. The math pointed to one inescapable truth. If everything is moving away now, it must have all started from a single point. That's the heart of the Big Bang Theory. Space itself began expanding from an unimaginably hot and dense state. Before that, there was no time, no space, nothing. It also explains something strange. Why the night sky is mostly dark. If the universe were infinite and eternal, every direction should shine with starlight. But much of the universe is invisible, simply because light hasn't had time to reach us yet. And beyond a certain point, about 14 billion light years, galaxies move faster than light, vanishing forever from our reach. Even today, the most advanced telescopes confirm this. The universe is expanding everywhere. But if it's the same from all points, why does every galaxy seem like the center? Here's the trick. Imagine dots on a balloon. As the balloon inflates, each dot moves away from all the others. If you focus on just one dot, it looks like everything else is moving away from it. But move your focus to any other dot, and you'll see the same thing. That's how it works in space. Every point sees itself at the center, but there is no true center, just uniform expansion. And here's the wild part. Galaxies aren't flying through space like spaceships. They're mostly sitting still while space stretches around them. That's how they can appear to move faster than light without breaking the rules. Einstein's speed limit applies to objects moving through space, not space itself. A galaxy 15 billion light-years away might be moving away from us faster than light, not because it's speeding through space, but because the space between us is growing so quickly. This balloon analogy isn't perfect, though. Balloons expand into the room around them. The universe doesn't. There's no outside for it to expand into. Space grows from the inside out, with no edge, no boundary. This is intrinsic expansion, not needing extra dimensions to grow into. No matter where you are in the universe, expansion looks the same. Every civilization that looks up will find the same redshifts, the same patterns, the same cosmic story. And it all began in an instant of pure energy, 13.8 billion years ago, when the universe was smaller than a proton. The temperatures were so extreme, our physics breaks down trying to describe it. And then, expansion began. The first moment of the universe is beyond human understanding. There was no space, no time, nothing. Space and time came into existence with the universe. Scientists call this moment the Big Bang, though it wasn't a bang in any normal sense. It wasn't an explosion in space. Space itself began to expand. In the first tiny fraction of a second, something incredible happened: inflation. The universe grew faster than anything we've ever measured. In less time than it takes light to cross a proton, the universe expanded by a factor of 10 superscript 2. Areas smaller than atoms suddenly stretched to the size of basketballs. This rapid expansion explains why the universe looks so uniform. Distant parts of the sky, too far to ever exchange signals, still have nearly the same temperature. Inflation stretched tiny, smooth regions to cosmic sizes. After inflation, the universe stayed incredibly hot and dense. For about 380,000 years, space glowed like a star. Free electrons scattered light in every direction, making the universe a glowing fog. Then came recombination, electrons paired with nuclei to form atoms. Suddenly, light could travel freely. Space became transparent. That light still exists today. We call it the cosmic microwave background, a faint glow filling the sky in every direction. It's the oldest light we can see, a snapshot of the universe as a baby. Its tiny temperature ripples match Big Bang predictions exactly and show where galaxies would later form. Since then, the universe has expanded by a factor of about 1,100. A region just a mile wide back then now spans over 1,000 miles. And this expansion is still accelerating. If everything is expanding, we can trace it backward to a beginning. About 13.8 billion years ago. Galaxies don't fly through space. They're carried by it, like raisins in rising dough. Imagine bread in the oven. As it rises, every raisin moves farther from the others. Not because they're moving, but because the dough itself is growing. The same is true for galaxies. Space expands around them, increasing the distances between them, while the galaxies mostly stay still in their local regions. And expansion is consistent. Every region of space grows at the same rate. That rate is about 70 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light-years, space grows by 43 meters per second. So a galaxy 100 million light-years away moves away at 1,300 meters per second. 1 billion light-years away, 13,000 meters per second. The farthest galaxies we can see? Almost light speed. Why so fast? Because while each region of space grows slowly, those effects stack up over billions of light-years. Galaxies don't move faster than light through space. Space itself stretches between us and them. That's why galaxies can appear to exceed light speed without breaking Einstein's rules. His theory only forbids objects from traveling faster than light through space, not the expansion of space itself. Imagine two ants crawling slowly on an inflating balloon. They hardly move, yet the distance between them grows rapidly. That's how galaxies behave. Most drift slowly, but space around them expands fast enough to separate them at superluminal speeds. This leads to a mind-bending idea, a cosmic horizon. Galaxies farther than about 14 billion light-years are receding faster than light. Their light will never reach us. They exist, but are forever out of sight. This boundary is called the Hubble horizon, and it gets stranger. Some galaxies we can see today will eventually vanish beyond this horizon. In the distant future, more and more of the universe will disappear from view. The night sky will grow darker as galaxies silently slip away. Even light from closer galaxies is stretched. Imagine a galaxy 8 billion light-years away. It sends out blue light, but as that light travels through expanding space, its wavelength stretches. Blue becomes green, then red, then infrared. This is called cosmological redshift. It's different from Doppler redshift, which comes from motion. Cosmological redshift is caused by the stretching of space during the light's journey. It tells us exactly how much the universe has expanded since the light was emitted. But space expansion causes a strange paradox. Light from the most distant objects took 13.8 billion years to reach us. Yet today, those galaxies are not 13.8 billion light-years away. They're about 46 billion light-years distant. Why? Because space kept expanding while their light was in transit. This creates the observable universe, a sphere centered on Earth, 46 billion light-years in radius. Everything inside it is potentially visible. Everything beyond it is forever hidden. No matter how advanced our telescopes become, this cosmic boundary can't be crossed. Beyond it may lie infinite galaxies, alien civilizations, or even other universes. But expansion ensures we'll never know. The structure of the entire universe, its true size, shape, and contents, remains a mystery. It might be infinite. It might loop back on itself like the surface of a sphere. But whatever lies beyond our cosmic horizon is sealed off by the expanding fabric of space. The observable universe is shrinking, not in size, but in the number of galaxies we can see. As expansion speeds up, galaxies near the edge of visibility move away faster and faster. Eventually, space pulls them beyond the point where their light can ever reach us. When that happens, they vanish from our universe forever. Right now, we can observe about 2 trillion galaxies, each with hundreds of billions of stars. Altogether, that's more stars than all the grains of sand on Earth's beaches, millions of times over. Yet that's only a small glimpse. Most of the cosmos lies beyond our horizon, hidden by the limits of light and time. The oldest light we can detect comes from the cosmic microwave background, emitted 380,000 years after the Big Bang. Before that, the universe was opaque, filled with hot plasma that blocked light. No telescope, no matter how advanced, can see beyond that fog. To study earlier moments, scientists rely on gravitational waves or theoretical physics. Our observable universe grows outward at the speed of light, but expansion outpaces this growth. As a result, the number of visible galaxies is actually shrinking. In the far future, only the galaxies in our local group will remain visible. The rest will fade away, leaving a lonely sky. As light travels through expanding space, it stretches, a phenomenon known as cosmological redshift. Imagine a wave drawn on a deflated balloon. Inflate the balloon, and the wave stretches. The same thing happens to light. Its wavelength increases, its color shifts toward red, and its energy drops. This stretching reveals a powerful truth. Light from distant galaxies carries unique fingerprints, spectral lines from hydrogen, helium, and other elements. These lines always appear at exact wavelengths. But when this ancient light reaches us, those lines are shifted to longer wavelengths. For example, hydrogen's bright red line at 656 nanometers might appear at 700 nanometers or beyond. A redshift of 1 means the universe has doubled in size since the light was emitted. A redshift of 10 means the cosmos has grown more than 11 times larger. Different types of light shift in dramatic ways. Ultraviolet becomes visible. Visible turns into infrared. X-rays stretch into the radio wave range. That's why telescopes like James Webb observe in the infrared to detect ancient galaxies whose light has been stretched over billions of years. Cosmological redshift also reveals distance. The more stretched the light, the farther it's traveled. That's how astronomers map the three-dimensional structure of the universe. These maps show how galaxies clump together over time and how expansion affects empty space, not the regions where gravity holds things together. The most extreme redshift comes from the cosmic microwave background. That ancient light has been stretched by a factor of 1,100 since it was first emitted, transforming it from visible to faint microwave radiation. But something even more mysterious is driving the cosmos apart: dark energy. In 1998, scientists studying distant supernovae expected to see that expansion was slowing down due to gravity. Instead, they saw something shocking. Expansion was speeding up. A force stronger than gravity was pushing the universe apart. This force, now called dark energy, acts only in the vast, empty stretches between galaxy clusters. It doesn't affect tightly bound structures like galaxies themselves. But in the voids, it dominates. Dark energy now makes up about 68% of the universe. Ordinary matter, the stuff we can see, makes up less than 5%. The rest is dark matter, another unknown component. That means 95% of the universe is made of things we don't fully understand. Some theories suggest dark energy is a property of space itself. Others propose it arises from hidden dimensions or quantum fields. Recent data even hints that it might evolve over time, growing stronger or weaker. If that's true, it could change everything we know about the future of the universe. If dark energy grows stronger, it could eventually tear the universe apart, ripping galaxies, stars, and even atoms to pieces in a dramatic end called the Big Rip. For now, dark energy remains invisible and unexplained, but it shapes our cosmos, accelerates its expansion, and may ultimately decide how everything ends. The universe is mostly made of something we can't see or detect, yet it controls everything. Imagine counting every star, planet, moon, and black hole. Add all the dust, gas, and galaxies combined, and you'd still have less than 5% of the universe. The other 95% is made of two invisible forces: dark matter and dark energy. Dark matter makes up 27%, while dark energy dominates with 68%. Neither emits light or interacts with electromagnetic forces. They reveal themselves only through gravity. Among them, dark energy is the bigger mystery. Unlike dark matter, it doesn't clump or gather. It's evenly spread across space. Every region of the universe has the same amount of it. And as the universe expands, the total dark energy increases, as if new energy appears out of nowhere. This defies everything we know about energy conservation. Though its density is tiny, just a few hydrogen atoms worth per cubic yard, the total across the cosmos outweighs all visible matter by more than tenfold. Scientists think dark energy might be the energy of empty space itself, caused by quantum effects. Quantum physics says that even nothing is alive with particles popping in and out of existence. But the math doesn't add up. Quantum theory predicts far too much energy, off by a factor of 10 superscript 2, the worst mismatch in science. So maybe dark energy has another origin. Other theories say it could come from hidden dimensions, or that it changes over time. Recent observations hint that dark energy may indeed be evolving, a clue that could rewrite the laws of physics. Because dark energy dominates the cosmos, ordinary matter, the stuff that makes stars, planets, and us, is just a cosmic afterthought. Everything we can see or touch is part of that small 5%. It's a humbling thought. We are made of rare material in a universe ruled by the unseen. But even beyond dark energy, a new puzzle has shaken modern cosmology, the Hubble tension. Two precise methods of measuring the universe's expansion rate give conflicting answers. The first method uses the cosmic microwave background, the ancient light left from the Big Bang. It suggests the universe expands at 67 kilometers per second per megaparsec. The second method, using nearby stars called Cepheid variables, gives 73 kilometers per second per megaparsec. A 9% difference, small but far beyond the margin of error, means something fundamental is missing from our understanding. Both results are confirmed by multiple teams using independent techniques. If the lower value is right, distant galaxies should appear closer than they do. If the higher one is right, our early universe models must be wrong. Either way, the numbers don't fit. The James Webb Space Telescope was expected to solve this mystery. Instead, it deepened it. Webb's unmatched precision confirmed that local measurements are accurate. Galaxies really are expanding faster than the early universe predicts. Webb studied hundreds of Cepheid stars in distant galaxies and found results that match Hubble's within 1%. This rules out measurement errors. Now astronomers face two options. Either the early universe behaved differently, or unknown physics are at play. Webb even detected tiny variations in expansion rate across space, hinting that dark energy might not be perfectly uniform after all. If the higher expansion rate is correct, the universe could be 1 billion years younger than we thought. That changes everything, from galaxy formation to the ultimate fate of the cosmos. As Nobel laureate Adam Rees says, this crisis may be our biggest opportunity, a sign that we're on the edge of discovering new physics. Some theories suggest early dark energy, a force that briefly influenced the universe's growth, or that gravity behaves differently on cosmic scales. Whatever the answer, it's clear, our current model of the universe is incomplete. Even the universe's baby picture, the cosmic microwave background, adds to the mystery. This ancient glow comes from 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. That light has stretched for over 13 billion years and still fills space today as faint microwaves. Its near-perfect uniformity reveals a crucial clue. Regions billions of light years apart share the same temperature, something only explained by cosmic inflation, a burst of expansion faster than light in the universe's first instant. This snapshot reminds us, the cosmos began in brilliant simplicity, yet its true nature remains deeply mysterious. Dark energy, dark matter, and the Hubble tension all point toward one truth. The universe is far stranger than we ever imagined. Tiny temperature variations in the cosmic microwave background reveal where the first galaxies were born. Slightly warmer regions held more matter, which gravity later pulled together into the galaxies and clusters we see today. This ancient light acts as a blueprint for the entire structure of the universe. By studying these temperature patterns, scientists can measure the universe's key properties with astonishing precision. Space appears flat to within 1%. The universe is 13.7 billion years old, and its contents break down into 26.8% dark matter and 68.3% dark energy. These same measurements predict an expansion rate of 67 kilometers per second per megaparsec, about 9% lower than what telescopes observe locally, the core of the Hubble tension. The analysis of the cosmic microwave background depends on understanding how expansion changed over billions of years. Even tiny shifts in that history leave visible traces in the temperature map. The standard cosmological model, with dark matter and dark energy, explains nearly everything with amazing accuracy. But it can't reconcile the difference between ancient and modern expansion rates, hinting that something is missing from our picture of the cosmos. The Planck satellite has mapped these temperature variations to incredible precision, better than 1 part in a million, confirming the model's predictions while emphasizing its limits. Yet the microwave background can't show us the first 380,000 years after the Big Bang, when the universe was still opaque. During that hidden era, space underwent the most explosive expansion in history, cosmic inflation. In a fraction of a second, smaller than the time light takes to cross a proton, space expanded faster than anything known to physics, by a factor larger than the total number of atoms in the observable universe. Alan Guth proposed this idea in 1980 to explain why the universe appears so uniform and flat, even though distant regions could never have exchanged light or information. Inflation stretched tiny, uniform patches of space to cosmic scales, smoothing out any irregularities. This expansion was driven by a mysterious inflation field, or inflaton, which filled space with enormous energy. When inflation ended, the field decayed, releasing its energy as the hot plasma that became the early universe. Quantum fluctuations during this period were stretched to vast scales, seeding the formation of all future structure, galaxies, stars, and planets. Without inflation, the universe would be smooth and lifeless. If inflation lasted just 60 e-foldings, space would have grown by a factor of 10^1, and most models suggest far more. This extreme stretching flattened space so completely that any original curvature became undetectable. Regions now billions of light years apart once shared the same tiny origin, explaining the cosmic microwave background's near-perfect uniformity. When inflation ended, a process called reheating flooded space with matter and radiation, the true beginning of the hot Big Bang. Evidence for this event comes from the detailed temperature patterns in the microwave background, which match exactly what inflation predicts. Still, inflation remains theoretical since we can't observe it directly, only its aftereffects. Scientists now search for new evidence, such as primordial gravitational waves, ripples from inflation that could leave faint signatures in the microwave background's polarization. Detecting them would be powerful proof that inflation really happened. Inflation also ties into the geometry of the universe, the shape of all reality. Space can be flat, closed, or open, and its shape determines the cosmos's ultimate fate. A flat universe extends forever, with parallel lines that never meet. Expansion slows but never stops. Galaxies drift apart endlessly. A closed universe curves like a sphere, where expansion eventually reverses, ending in a catastrophic big crunch. An open universe curves outward like a saddle, where expansion accelerates forever, stretching space until it becomes cold, dark, and empty. The balance of matter and energy decides which geometry rules our reality. And right now, the evidence shows we live in a universe that's almost perfectly flat, stretched smooth by the incredible burst of inflation at the dawn of time. Low density gives space an open shape, while a precise critical density creates a perfectly flat universe. About 6 protons worth of mass in every cubic yard of space. Observations show our universe is astonishingly close to this balance point. The cosmic microwave background confirms that space is flat to within 1% accuracy, as if the cosmos is balanced on a knife's edge between collapse and endless expansion. For decades, scientists wondered why the universe's density is so perfectly tuned. The answer lies in cosmic inflation, a burst of exponential expansion moments after the Big Bang that stretched any initial curvature flat, like blowing up a balloon until its surface seems smooth. But dark energy complicates this picture. In a flat universe, gravity should gradually slow expansion. Instead, dark energy drives acceleration, meaning our universe expands forever and faster over time. The outcome depends on whether dark energy stays constant, strengthens, or fades. If it grows, it could tear everything apart. If it weakens, expansion could slow or even reverse. The balance between expansion and collapse depends on this critical density. Add just a bit more matter, and gravity wins, leading to a big crunch. Add less, and expansion runs away into a cold, empty cosmos. Our universe sits within 1% of that perfect balance, a cosmic coincidence so precise that even a 1 in a billion variation in the early universe would have made life impossible. Inflation explains this fine-tuning. It drove the universe toward critical density regardless of its starting value. Yet, as the cosmos expanded, matter thinned out while dark energy stayed constant, slowly taking over. Today, dark energy makes up about 68% of the universe, with matter just 32%. Though the total density slightly exceeds the critical value, dark energy's repulsive force dominates, causing accelerated expansion. This balance raises deep questions. Why do the constants of physics have the values they do? Why does the universe seem designed for life? Some scientists suggest a multiverse, countless universes with different physical laws, where we happen to exist in one that supports life. Others believe deeper, undiscovered physics might naturally push cosmic density toward the critical value. A radical new theory offers another explanation. Our universe might be growing by absorbing smaller, baby universes. Physicist Jan Ambien from Copenhagen University proposed that quantum fluctuations constantly create tiny universes that merge with ours, expanding it like soap bubbles joining together. Each collision adds more space, mimicking dark energy's effects, without needing mysterious, invisible forces. These baby universes would exist in higher dimensions, invisible except through gravity. Ambien's calculations show that their merger rate matches the observed acceleration of cosmic expansion even better than standard dark energy models. In quantum theory, empty space teems with energy fluctuations. Some may create pocket universes smaller than protons, most of which quickly merge back into ours. This constant merging could explain why space stays flat and why our universe seems perfectly balanced for life, perhaps the result of cosmic natural selection, where stable universes outlast unstable ones. Still, this idea is highly speculative. There's no direct evidence of baby universes or higher dimensions. Detecting them would require observing gravitational ripples from universe mergers, an almost impossible task with today's technology. Yet, the concept reshapes how we see reality. If universes constantly merge, then our cosmos is just one bubble in an infinite foam of realities, forever growing through cosmic collisions. Critics argue it replaces one mystery with another, but it pushes us toward a deeper truth. Maybe our universe's expansion is driven not by dark energy, but by the hidden dance of parallel worlds. Some scientists suggest that dark energy could come from interactions between our universe and nearby parallel realities. If other universes contain different amounts of matter and energy, gravity might leak between dimensions, creating the illusion of acceleration in our space. In this view, dark energy isn't a mysterious force. It's a gravitational influence from unseen universes. String theory supports this idea. It predicts extra dimensions where gravity can move freely, while our familiar matter and forces remain confined to a three-dimensional membrane. This setup allows subtle gravitational communication between universes even when everything else remains isolated. These multiverse models reveal astonishing possibilities. Some universes could have stronger gravity, others different kinds of matter and forces. Their interactions might drive cosmic expansion in ways that mimic dark energy. In eternal inflation models, new universes constantly emerge from quantum fluctuations, and each new creation could influence the geometry and expansion of all universes collectively. The anthropic principle ties this to life itself. Among countless universes with varying expansion rates, we naturally exist in one with the perfect conditions for galaxies, stars, and life. Universes that expand too quickly or too slowly remain lifeless. Yet, these ideas face a huge challenge. Parallel universes are impossible to observe directly, making such theories hard to test scientifically. Critics argue that the multiverse is more mathematics than science, since it can't be verified by experiments. Still, some researchers hope to find traces of interdimensional collisions in the cosmic microwave background, faint patterns left by other universes brushing against ours. Future telescopes might one day detect these fingerprints. If true, the multiverse reshapes our understanding of existence. Our universe becomes just one bubble in an infinite cosmic foam. The expansion we see would simply be a local event within this vast structure. The story of expansion began with Alexander Friedmann, who in 1922 derived equations from Einstein's relativity, showing that the universe cannot stay static. It must expand or contract. These Friedmann equations describe how the universe's scale factor changes with time. As this cosmic measuring stick grows, distances between galaxies increase even though galaxies themselves barely move. Expansion depends on the universe's energy density. Matter and radiation create gravity that slows expansion, while dark energy provides negative pressure that speeds it up. In the early universe, radiation dominated, slowing expansion sharply. Later, matter took over. Around 5 billion years ago, dark energy became dominant, and expansion began to accelerate again. The metric tensor in relativity describes how space itself stretches while time flows normally. Galaxies don't move through space. Instead, space expands around them. The Robertson-Walker metric refined Friedmann's work, showing that if the universe looks uniform everywhere, all its complex geometry can be described with a single function, the scale factor. The Hubble parameter measures how fast this expansion happens, velocity divided by distance, forming the linear relationship Hubble discovered. As light travels through expanding space, its wavelength stretches, causing the cosmological redshift we observe in distant galaxies. By tracing this expansion backward, scientists estimate the universe's age at 13.8 billion years. The critical density emerges when Friedmann's equations balance gravity against expansion, the exact point between eternal growth and eventual collapse. Its value changes as expansion evolves. Dark energy enters these equations with negative pressure, producing the repulsive force that drives today's accelerated expansion. This elegant mathematics challenges our intuition. Space expands everywhere at once, without a center or an edge. Every observer, no matter where they are, sees all distant galaxies moving away, making it appear as if they are at the center. But there is no true center. Expansion affects all regions equally. Imagine stretching an infinite sheet of graph paper. Every square grows, and each one sees all others receding. Or picture dots on a balloon's surface. As it inflates, every moves away from the rest, yet none lie at the center. The universe behaves the same way, expanding uniformly in all directions, with no edge, no boundary, and no special location. Even if the universe is finite, it could curve back on itself like Earth's surface, endless to travel, yet without borders. This is the strange, beautiful geometry of our ever-expanding cosmos. The surface of a sphere has a finite area, but no edges. Likewise, the universe could have finite volume, yet no boundaries. The Big Bang didn't happen at a single point in space. It happened everywhere at once. Space itself was once compressed to zero size, and as expansion began, every point grew simultaneously. There was no explosion into empty space because the universe is all the space that exists. This centerless expansion explains why we see the cosmic microwave background evenly in all directions. That ancient light, released when the universe became transparent 380,000 years after the Big Bang, reaches us from every direction because expansion affects all regions equally. If the universe had a center, the radiation would appear stronger in one direction, but it doesn't. The same principle shapes the universe's fate. With no center or edge, dark energy accelerates expansion everywhere at once, pushing galaxies apart faster and faster, over unimaginable timescales. This leads to a bleak prediction. The universe will grow colder, darker, and emptier until nothing remains but fading energy. In about 100 trillion years, the last stars will burn out. Expansion will stretch matter so thin that gravity can no longer form new stars. The cosmos will drift into the era of darkness, a silent, starless void. White dwarfs and neutron stars will cool into invisible remnants. Even black holes will eventually evaporate through Hawking radiation, though it will take longer than the number 1, followed by 67 zeros in years. The most massive black holes will survive far longer, but even they will fade, leaving only stray particles, electrons, neutrinos, photons, scattered across infinite space. As everything spreads apart, the universe's temperature will drop near absolute zero. Entropy, or disorder, will reach its maximum, and all motion, all change, will cease. This is the heat death of the universe, a state of perfect stillness where no work or life is possible. If dark energy remains constant, this cold death is inevitable. But if it grows stronger, expansion could eventually tear apart galaxies, stars, planets, even atoms, in a violent end known as the Big Rip. If it weakens, gravity might someday reverse expansion, leading to a big crunch, collapsing everything back into a singularity, possibly triggering another Big Bang. For now, evidence suggests dark energy is stable, meaning the universe is headed for a long, cold fade into nothingness. Yet beyond our cosmic horizon, 46 billion light-years away, lie regions forever beyond our reach. Expansion carries them away faster than light can travel. These unseen realms might host strange physics, alien worlds, even copies of ourselves. If the universe is infinite, then every possible configuration of atoms repeats endlessly. Somewhere out there, another version of you exists, thinking these same thoughts. But as dark energy accelerates expansion, more galaxies slip beyond visibility than new ones appear. Future observers will see only a handful of nearby galaxies, unaware that the night sky once held trillions. The cosmos will grow increasingly lonely as its wonders vanish one by one. Beyond our reach, entire domains may follow different laws of physics, some with stronger gravity, others expanding far faster, or lacking dark energy altogether. These regions form an infinite cosmic library, filled with realities we can never read, each one a different experiment in the grand story of existence. Beyond our cosmic horizon, advanced civilizations might exist, beings billions of years ahead of us, capable of bending space and time. They may have mastered physics beyond our imagination, or even learned to communicate across horizons. Yet those regions could also harbor unimaginable dangers, black holes larger than solar systems, or quantum disasters that could erase reality itself. Some theories go further, proposing that beyond our horizon lie not just distant regions of space, but entirely separate universes, each with its own laws of physics and dimensions. Together, these realities form the multiverse, an endless collection of cosmic possibilities where every form of existence might unfold. But this idea challenges science itself. If we can never observe what lies beyond our reach, can we ever claim to understand the universe? The cosmic horizon marks the ultimate limit of knowledge, a reminder that expansion forever hides parts of reality from view. According to logic, expansion should slow over time because gravity pulls matter together. Yet observations reveal the opposite. Cosmic acceleration began about 5 billion years ago, driven by mysterious dark energy. Early on, matter's density was high enough to slow expansion, but as the universe grew, gravity weakened while dark energy stayed constant, eventually taking over. Today, dark energy makes up about 68% of the universe, and its influence keeps growing. Recent data from the Dark Energy Spectroscopic Instrument hints that this energy might be changing over time. If it strengthens, expansion will accelerate until it tears apart everything: galaxies, stars, even atoms, in a final big rip. Galaxy clusters would disperse first, followed by galaxies, solar systems, and finally, the fabric of matter itself. If dark energy weakens instead, expansion might halt and reverse into a big crunch, collapsing all existence into a new singularity, perhaps setting the stage for another Big Bang. Some models even suggest a cyclic universe, endlessly oscillating between expansion and contraction. Each phase would birth a new cosmos, erasing traces of the previous one. As dark energy dominates further, space-time could expand exponentially, mirroring the rapid inflation that followed the original Big Bang. Eventually, dark energy will isolate our local group of galaxies from the rest of the universe. Every other galaxy will vanish beyond our cosmic horizon, leaving us on a lonely island surrounded by infinite emptiness. Even the cosmic microwave background, our baby picture of the universe, will fade as its wavelength stretches beyond detectability. The mystery deepens when we realize that dark energy may be linked to the quantum nature of empty space, a built-in feature of reality itself. And it isn't alone. The universe's structure also depends on another invisible force, dark matter. While dark energy drives expansion, dark matter sculpts the universe. Making up about 27% of all energy, it outweighs normal matter 5 to 1. Though invisible, it anchors galaxies together through gravity. Without it, the universe would be smooth and structureless. The cosmic microwave background reveals tiny temperature variations, ancient fingerprints of dark matter's influence. Over billions of years, these small fluctuations grew into the cosmic web of galaxies we see today. But dark matter's identity remains unknown. It can't be normal atoms, photons, or neutrinos. Candidates include WIMPs, weakly interacting massive particles, axions, or even primordial black holes, exotic relics of the early universe. Each possibility could change our understanding of cosmic expansion in subtle, profound ways. Dark matter forms the invisible scaffolding of the cosmos, guiding how the universe expands and evolves. It stretches into vast filaments hundreds of millions of light years long, connecting dense nodes where galaxies cluster. In areas rich with dark matter, gravity slows expansion enough for stars and galaxies to form. In emptier regions, expansion dominates, leaving behind cosmic voids that remain nearly empty. This unseen matter shapes how galaxies spin and stay together. Without dark matter's gravitational grip, expansion would tear them apart. Simulations show that dark matter forms halos, filaments, and clusters, structures that grow as gravity pulls them tighter while expansion pushes them apart. This delicate tug-of-war built the universe's grand design. But the future belongs to dark energy, not dark matter. As expansion accelerates, dark energy will overpower gravity, halting the birth of new structures. The cosmic web itself will fade as the universe stretches faster than matter can gather. Astronomers map dark matter using gravitational lensing, watching how its gravity bends light from distant galaxies. These patterns reveal how dark matter has shaped cosmic growth across time, from the early universe to now. Yet, even this makes up only part of reality's vast inventory. From quantum ripples smaller than atoms to cosmic filaments spanning billions of light years, expansion links the tiniest scales to the infinite. At subatomic levels, Quantum fluctuations blink in and out of existence within unimaginable fractions of a second. At the largest scales, expansion moves galaxy clusters across billions of light years. Between these extremes, different forces dominate. Atomic and nuclear forces overpower expansion at small scales. Gravity rules at planetary and galactic scales, and expansion takes over the vast spaces between galaxy clusters. Our Milky Way, 100,000 light-years wide with 400 billion stars, remains bound by gravity, unaffected by cosmic stretching. But beyond galaxy clusters, expansion reigns supreme, pushing everything farther apart. The cosmic web, the universe's largest structure, connects clusters through filaments of dark matter and gas, shaped by the same expansion that began 13.8 billion years ago. From the smallest quantum tremor to the grandest cosmic motion, expansion unites every scale of existence. Quantum ripples became galaxies. Gravity shaped them into stars. Dark energy now dictates their fate. The timescales are equally staggering, from quantum moments that last less than a blink of light to cosmic ages that span trillions of years. If the multiverse exists, our universe may be just one bubble among countless others, each expanding with its own laws of physics. Across these realities, expansion might repeat endlessly, a hierarchy of universes within universes. And yet, one question remains. What does it mean for the universe to expand into nothing? The answer is profound. Space doesn't expand into anything. It simply creates more of itself. Every atom, every star, and every thought rides this self-generating fabric into an unknown future. You are part of this cosmic equation. The atoms that form you make up less than 5% of reality. The rest is unseen dark matter and dark energy. Your very existence depends on expansion being perfectly balanced, not too fast for galaxies to form, not too slow for life to evolve. Each breath you take happens in a universe that's stretching around you. The light you see from distant stars began its journey billions of years ago, redshifted by the growth of space itself. You exist within an expanding galaxy, inside an expanding cluster, within an expanding universe, perhaps one of infinite others. One day, this expansion will carry even the last atoms of your body into a dark, frozen cosmos. Yet right now, you live in a rare, vibrant era, when stars still shine, galaxies still dance, and life can still exist. We know space is expanding. We can measure it, model it, and trace it back to the Big Bang. But what drives it, and why, remains one of the greatest mysteries in existence. Perhaps the real answer isn't out there, but within us. We are the universe becoming aware of its own expansion. So the ultimate question isn't what the universe expands into, but why it expands at all. You are part of that unfolding mystery, a conscious ripple in a universe that stretches endlessly toward the unknown.